Hello ladies and gentlemen, welcome back to what is going to be the fourth lab that we're going to be doing. So today I'm going to be focusing on some of the spatial descriptive techniques that we carried out within the lecture, but I'm going to be showing you first how we use some of those within the R Studio environment, and then in the second lab video that you're going to receive, we're going to be doing some calculations within ArcMap, ArcGIS. Okay, so the first thing that you want to do is open up your R Studio. Hopefully you've been able to download the code from the Blackboard website and basically place it into a folder wherever you want. Then you can just go into the folder that you need to go to. I'm going to open up Lab 3. Here we go, and now we've got the R script open within our studio, and we're able now to start to begin to progress with some of the things that we want to cover today. So first of all, what we're going to do is just set the folder. So I know some of you have had a couple of problems with this. You need to make sure that you've got the RStudio API actually installed. So if you haven't, then just click run that line. Remember, all I'm doing here is I'm pressing Control Enter to run that single line that the cursor's on. So just here, see where the cursor is in the script? And I can just go down here now that we've got it installed, and I can basically press Control Enter like this, and what that's doing is saying go to the RStudio API, get me the source editor context path, and then basically I'm saying just give me the directory name of that full string of the file path. So I showed you before that a string is basically text, and the path in this case is just the path to where my code is. So this is just the directory folder. So it's saying it's on the C drive, it's in users, it's in Edward, it's in Dropbox, it's in teaching, it's in 300 quant methods, it's in spring semester 2021, it's in week 4, and it's in the lab. Okay, and then that will be the directory for the lab3.r script. And once we've got that directory, we can just say set the working directory to the folder, just like this. Okay, so hopefully that's fairly clear to you now, and that means we can just grab any data that we want from within that specific folder. See, we've got these 2 CSV files that we'll want to load in later in the session, and now it knows that we're working in this folder. It can just grab those particular files when it wants them. Great, so you'll remember within the lecture we covered a wide variety of different spatial statistical areas. So we covered measures of central tendency, dispersion, and shape. What we're going to cover first here is measures of central tendency. So we're going to need those 2 data sets that we want to pull in. What we're going to focus on is actually creating the mean center, which is something which we covered within the lecture, okay? So there's two different ways that we can do that. It depends on how you measure distance. So I mentioned this a couple of times within the lecture. We're going to get into that later, but for now, at least the math for how we calculate the mean center is pretty standardized, so that should be fairly straightforward. Now what I have are 2 separate CSV files. It's just some spatial data, okay? It contains an XY coordinate and a latitude, longitude coordinate. So this is basically a projected coordinate in meters. This is the WGS300 global latitude, longitude coordinates, which is measured in degrees. And then we have cities here. It's actually teams for baseball and the state name, okay? And that's for 1900, and then we basically have the same for the year 2000. Obviously, there's more baseball teams by then. It's less about the baseball teams part, just more about the fact that we've got some different lat-long coordinates for cities, essentially for 2 different time periods. Now, we covered before how to read in a CSV file. So if you just remember that read CSV basically will take an argument for the file name. So here what we're doing is we're just saying go into our working directory, and I want to use read.csv, and I want to load the file named bb1900.csv. And when I do that, it places that one data set into the R environment up here, okay? So we've got that same data that I showed you when I was in the Excel spreadsheets, for both 1900 and for 2000, okay? So now that we've got those, we can calculate the mean center. So if you look at the tables, you'll notice that we've got both lat long and xy. We can use both for this particular circumstance. If you want it in meters, then it makes, if you want it in the projected coordinate, it makes more sense to use the xy. If you just want the latitude, longitude coordinates in degrees, then you can use the lat longs. Okay, the key point is that in order to get the mean center, we need to get the mean of the x and the y coordinate. Okay, so let me just go back to how I did this within the lecture so that I can remind you. You'll remember that we went over this particular slide. So I think this is slide 34 out of 54. And essentially what we're doing is we're just saying, okay, sum up all of the xi coordinates divided by the number of coordinates that we've got in the data set, n, and then give me the average. So the mean x bar value of the coordinate is whatever this the result of this equation is. And then we can do the same for the y coordinate as well. Okay, so rather than me go through this again, which you know how to do now, you just need to sum xi and divide by the length of the number of data points. I can just use the inbuilt function. Okay, so I can just say go into the baseball teams for 1900 data set BB19 that we've got this one up here. And then what I want to do is go into the latitude column, so it's this one here, which is numerical, and then I just want you to find the mean value, okay? So if you're still unsure about using that particular function, you can just look at the help menu for the arithmetic mean here, and it will provide you with an understanding of the different arguments that you can provide. So in essence, when we do this, what we end up with are a set of mean center coordinates for all of the cities for 1900 that I just showed you, which here is basically 40.48 degrees and minus 79.55 degrees for the latitude and the longitude coordinates, okay? And then we're able to do basically exactly the same. So we're going to do it now for the year 2000 data set of cities that we've got. And as you'll remember from the session that we did, by that point, there's many more cities across the United States. In particular, there are more cities which have occurred in the West and the South, for example. And therefore, in this case, more baseball teams. So we're able to take the mean latitude, longitude coordinates here, and that just provides us with an estimate of where the mean center is for the year 2000 database. And basically, you can see that there's been quite a substantial shift. So we've seen a slight move to the south, so from 40.48 degrees to 38.49 degrees, but then really quite a dramatic shift westwards because of expansion of the US into the western parts of the contiguous United States. So minus 92.40 degrees for that coordinate for the mean center. Great, so that just provides you with a bit of an understanding of the mean center for those two different data sets. We can actually plot these, so you'll be familiar with plot because we used that function in the previous sessions that we did and in the assignments. So I've just shown you the help menu here where plot is basically generic XY plotting, generic being the key point here because it's not particularly attractive. It does what it says on the tin, it's dead easy to use, but it doesn't give you all of the beautiful functionality that you can get from the other packages, which many of us used in the previous sessions and the assignments, such as ggplot2. So anyway, just bear with me. I just want to plot these data points as like this in this kind of very generic way, and I'll help you produce a pretty map out of them later in the session. So anyway, here we have the plot that I mentioned for the latitude coordinates on the y-axis and the longitude coordinates on the x-axis, which makes sense. And these are all the plots for the cities. So essentially, this is for the year 2000. We can then use points, the function basically, which allows us to add more points to the existing plot, this time for that should be 1900 data points. So we'll use the arguments PCH and col to basically provide point characters and a color for what we'd like. So I think this is the point size. Let me just check that. And the other one is the color. Add points to a plot. So it's always good to check the README. So PCH is the plotting character, the symbol used. Okay, so this is basically just saying, it's probably saying just give me a different symbol from the other one that we plotted. And then the col is actually the color difference. Okay, so when we plot this, okay, what we get are red triangles for the 1900 year data, which is here mainly in the northeast, New England area, Midwest, whereas by the year 2000 we have all these other cities across the south and the west. And we can start to change those a little bit more if we want. We can add the mean centers. So basically what we're doing here is we're adding those mean values that we took up above. Can you remember here it had M in front of it for the mean longitude for 1900 and the mean latitude for 1900, the mean longitude for 2000, the mean latitude for 2000. And we're able to add them in. So basically for the 1900 year points, we've got a red, what is quite an ugly asterisk. And then for the year 2000, we have just a standard black asterisk. Okay, you can see how those points have moved quite substantially. Okay, so that's how you create a generic ugly map, in my opinion. Now let's create something that's a lot prettier and something which, you know, if you go on and you decide you want to do some mapping in R after this spatial statistics module, then you've got the code which I've basically given you in order for you to kind of get an understanding as to how to create these kind of beautiful maps using the command line. And actually it's really powerful because, you know, if I said to you, go off and recreate the map with new data in ArcGIS, ArcMap, you would basically have to sit there and probably click through the graphical user interface in order to recreate the map. Whereas as long as my input data is in the same structure, I can just literally change the input file and rerun the whole code. Just press Control, Shift, and Enter, runs the whole code, and then it will just generate the map output using the new data. So it's all nicely automated. And that really is the kind of strength of using this script-based analysis approach rather than using, say, a Minitab or SPSS or ArcMap, where you'll be using a graphical user interface and you have to click between the different commands. So I know it's a big leap up here to start using this, but it's such a powerful tool. So once we've installed the package, we just need to say, hey, RStudio, can you just go and get that package and bring it into my current workspace in RStudio? And that's what the library function does for ggmap. So if you want to read more about ggmap, you're welcome to. It's part of the ggmap package. It allows you to plot a ggmap object, and there's just so much that you can do with this. So the help menu is obviously huge in comparison to the generic plotting which I showed you before. What we need to do before we create what's going to be a panel plot, so I want us to create a single image which has multiple maps in it for each of the different time periods, is we basically need to get the two data sets and put them together into a single data set, and then we can give that data set to the function. So what I'm going to do is I'm going to go into each one of these different data sets that we've got, BB19 and BB20. At the moment, it doesn't say anything about the year in here. So what I'm going to do is I'm just going to say, create me a variable. So in this data set, give me a variable, the $, and I want to call it year. Okay, so when I do that, I then go back in here and you can see it's added the year variable and it's allocated 1900 as a string for all of the cells, all of the rows across that particular data frame. And I can do the same for the year 2000. So now I have 1900 for this data set and the year 2000 for this data set. And now that we've got those 2 years, we can just basically push them together because they align, they've got the same number of vertical columns, they're all labeled the same. So it's just saying take the two side-by-side data sets and put them together into one single object, and that's what rbind does. Okay, so help rbind. This allows you to combine R objects by rows or column. So cbind would be by column. Here I just want to say take the BB19 and take the BB20 and just literally put them together vertically. And then when we get the all data, what we've got here is all of our data in a single data frame. Okay, so now we've gone from having 8 in the first data set and then 30 in the second data set, to having all 38 values that we of interest, also 38 points of interest in a single data set. And what we can also do is we can, before we plot, we can just create another data frame which contains all the mean data. So you remember we created the mean longitude, the mean longitude for 2000, mean longitude for 1900, and the mean longitude for 2000. And we created the mean latitude for 1900 and the mean latitude for 2000. And we can put them together along with the years. So this is just creating vectors out of these. They go in here. And then when we use the data frame function, which we used the last time, we're able to stitch them all together. Okay. So this C, remember, just concatenates whatever's in the brackets. So if we look at what ln is here, it's just got those values together in an array. And then when we put them all together in a data frame, they go from just here in this values part of the environment into this data frame part of the environment. So up here where it says data, and then you can see what we just stitched together. And it needs to be in the data frame structure so that we can give it to the function in order for us to create the nice pretty map, which I'm going to show you now. Okay, so we bound we created a binded version. Sorry, we created a combined version of all our data in a long data format, and then we created a mean data frame as well. Okay, so we have these two sets. Now what we're going to do is we're going to use ggmap, and we're going to use the qm plot, which is called the quick map plot. Great, I like quick things, I like easy, simple things. So qm plot is a good way for us to start to create a quick map. Yeah, you can look if you want to at all of the arguments, but I mean, it's a lot more complicated, so I just wouldn't worry about it for now. Just follow what I've done here and enjoy creating pretty maps. So what this essentially does is it says for the quick map plot function we're going to call, we want to plot the longitude and the latitude, and this will always take the plots in the first two parts of the first two arguments. So you see here x and y need to be the first two arguments you give it, and then you give it the data. Okay, so the data equals all data, and I've actually just written for you on the right hand side here. So anything that's hashed out basically explains specifically what I'm doing on that line, so it's hopefully dead clear to you. So that gives us the longitude and the latitude. We then tell it this is the data we want to map. We then, because this is a fancy pretty map, we need to tell it what type of background we would like the map to have, and it's going to go off to the web server online, and it's going to probably pull the map layer down, and then place that into our map. And here I've just said tone of background, so it's just a standard type of map background. And then for the color, I just want to state the point color that we want to plot in. Okay. Now before I worry you about this next point, let's just plot this map here. Because what this is doing is it's giving it the data, it's saying what our background is going to be, and we're saying what the color points we want to have. And then this facet wrap is basically just part of the functions that you're able to provide it. So you see it says facets here. You can pick facet wrap or facet grid. It just allows you to provide it with a variable, and it will create as many maps as you have for the values in that variable. So here we've got year, which we're using, and we're saying we want, we've got two different values in year. We've got 1900 and 2000, and we want it in one column, and we say let's go and create a map which will fit these dimensions. Okay, so here we go. It's a nice pretty map now. So this is the year 1900 with our cities over here in the northeast, New England area, and then into the Midwest. And then we've got the year 2000 cities down here, where we've got many more, all the way down into Florida, Texas, all the way across into the west, so Arizona, California, Seattle in Washington up in the northwest. Okay, so that's how we create that facet map that I'm talking about, where we're able to stitch together lots of different maps very simply. You know, I use these all the time, and I absolutely love producing these types of maps. So let me think. I've got a very quick example that I can show you for a paper that I've been working on of how we use these plotting functions. Okay, so you can add, this isn't a map, it's just a data frame, it's just a set of data, but this is how you create these beautiful facets. So you could have lots of different graphs in one overall plot to create that kind of beautiful look. So that was just a simplified way that we run the actual plot. We're just using the facet wrap, but we also want to add in an additional layer, which is our mean data points. Okay, so we're saying now add in an additional geometry point layer with the latitude and longitude coordinates x and y. We want to give it a particular shape, which is a diamond. We want to fill it yellow. We want to give it a size 3, so it's quite large. And we want to give it the data, which is the mean data. And when we do that, what we end up with is a kind of much prettier plot, which shows the mean center for those first sets of points, and then the mean center for the second set of points. And there's really quite a drastic mean between these two years, obviously separated by a century, due to population both moving westwards, southwards, and also growing quite significantly over that time. Okay, great. Let's move on to how we measure the Euclidean distance now. So I'm just going to quickly clear this so that you're able to focus on what we want to look at. So you'll remember that the Euclidean distance could be seen as the straight line path distance, the Pythagorean distance, as the kind of bird flies distance, all kind of refers to the same thing. But essentially what we're doing is we want to measure the distance between two particular points on a straight line. Okay, so let me just go and find this. We went over this before. We had the equation which we discussed in class here, and basically what we're going to do is we're going to take the two mean points. So we've got the mean longitude here for 1920 for 2000. And then we're going to subtract them in order to get the difference between them, and then that will form one of the sides of our right angle triangle. Let's just call it A here. And then we'll do the same for the latitude as well, and that's going to give us the B. And then when we add together basically the sum of, so the product of that calculation, so we need to square them, add them together, and then we take the square root. That's how we obtain the Euclidean distance between those individual points. Okay, so I'm able to do it here between, oh sorry, I did actually need quite a few of the data points that I created earlier in the script. So let's see if I can run this now. Great, so okay, 13 degrees difference between those two different points. Okay, and we measured that by using the straight line Pythagorean distance approach. Okay, that I went into quite a bit of detail here on. We are also able to measure different types of distance measure, and I mentioned before Manhattan distance is one where we wouldn't take the hypotenuse, so the straight line distance, the Euclidean distance, we would take the right angle distance, so the grid-based distance, so we need to go down the A and the B side here and get the distance for those two sides. So the way that we would do that is we would subtract the longitude values, the coordinates from themselves, and the latitude coordinates from themselves. And because these are potentially negative, we would need to take the absolute values. So if you just Google absolute, that will provide you with an understanding of this. I mean, you're just basically saying if it's negative, give me a positive number. And then when we actually add them together, we get the distance in degrees. So this is the Manhattan distance between those 2 points, which is obviously longer because the hypotenuse is obviously the straight line distance. And this time we've had to take a more elongated approach between those two different points. Okay. Great. Spatial measures of dispersion. So we're interested in taking the standard distance, for example, which I covered within the lecture. So let me just find that here. Standard distance, great. So this is generally how we need to calculate this. So it's analogous to the standard deviation. What we're going to do here is we're going to take the standard distance for the year 1900 data first. It's rather than me just giving you one giant equation, I'm going to break it down. Okay, so what we're going to do is we're going to do the numerator first, basically. So what we want to do is take each of the longitude values that we have within the 1900 data set, and we want to subtract the mean value. So xi refers to each of those rows that we have in that set of data for that one coordinate, the x coordinate, and then we're just going to subtract the mean value each time. And then what we're going to do is we're going to raise it to the power of 2, so square it, and then we're going to take the summation. Okay, sorry. And then basically that allows us to obtain the numerator values here. So x19 and y19, and then what we can do is we can then finish off this equation here by basically so we've got the products already, the sum of the squares, then we just need to add the x and the y values together, divide by the number of data points in the data set n, and then take the square root, so we go back to the original values. Okay, so when we do that, what we end up with is 6.79 or 6.8 when rounded degrees as the standard distance. Now obviously degrees aren't exactly the preferred measurement unit if you want to kind of have something a bit more meaningful. So I mean, in reality we would prefer to use meters here, so it would make more sense to use the XY coordinates, which you're fully welcome to do. I think the key point I just want to emphasize is that depending on the research question that you have and the coordinate reference system that you're using, you want to be very aware of the units that you're measuring in order for you to use a system that's sensible and kind of prudent with your kind of research aims, right? So if you're measuring distance, then you basically want to make sure that you've got it in preferably some sort of metric unit like meters, which is how I normally operate. And then we can basically just do exactly the same for the year 2000 if we want. So we take the sum of the square deviations from the mean for the longitude and then for the latitude for the year 2000, and we actually add these values into the global environment. And then we can just add them together, divide them by the length of the data points that we've got, and then take the square root. And when we do that, we end up with 17.26032, so 17.26 when rounded to two significant figures. So essentially, that provides us with, two decimal places. That provides us with the kind of code for actually delivering some of those spatial statistical methods that I mentioned within the lecture. I'm going to be following on now with a few examples within ArcGIS, ArcMap, in order for you to actually kind of do some of the more complicated equations, which I've saved you from doing in R. So we'll just use the inbuilt processing statistical toolboxes that are within that existing GIS platform. Okay, great. Well, it was very nice to see you again, ladies and gentlemen. Thank you very much for tuning in to this laboratory this week. There'll be another video, and then obviously there'll be the assignment this week that you'll need to complete. So I hope you're all doing well. I hope you're enjoying the course. I really hope that these are, interesting and exciting lectures for you. So please do let me know if you've got any problems. Thank you very much. Goodbye.